Hello everyone, welcome to my channel Essentials of Electronics. In today's video, we are going to discuss about some basic concepts of multivibrators and we'll discuss on one type of multivibrator. Before going into the mainstream of multivibrator, we must recall about the feedback system. In feedback system, we have two types of feedback, positive feedback and negative feedback. Isn't it? So what is a positive feedback? If the feedback signal and the input signal are in phase with each other, then we call them as positive feedback. So what kind of circuits are given with positive feedback is mostly oscillator circuits, multivibrators are given with positive feedback. The reason is oscillators and multivibrators are not fed with any separate input signal. Only the biasing voltage is given along with the components such as R, L and C help to generate the feedback signal by connecting either of these or in combination in the feedback signal. So these are the basic concepts of positive feedback, the basic conditions for positive feedback given by Barkhausen and hence the name. Barkhausen criteria are the product of the angle AV beta should be equal to 0 degree or 360 degree, and the modulus value of the product of AV beta is equal to unity. Yes, so these are the two Barkhausen conditions for positive feedback, and these oscillators generate waveforms if the biasing is proper along with the components connected in the feedback is suiting. The circuit will automatically generate sinusoidal waveforms or non-sinusoidal waveforms. So generally the circuits that generate sinusoidal waveforms are called oscillators, and the circuits that generate non-sinusoidal waveforms are called multivibrators. So we have discussed the types of oscillators in the previous videos. In today's video, the basics of multivibrators will be discussing. These multivibrators are operating in different states. Yes, so based on the states of operation, they are classified as astable multivibrator, monostable multivibrator, and bistable multivibrator. A stable multivibrator is one in which there are no stable states. The circuit operates without any stability state. So continuously the output waveform will be oscillating. In monostable state, one state will be a stable one and the other one will be in quasi-stable state. In bistable multivibrator, there are two stable states. So we will discuss a stable multivibrator. Yes, in the following video, we are going to discuss about the first kind of multivibrator, a stable multivibrator. So we have two transistors connected back to back in this manner with their emitters grounded in this manner. The RC resistor connected on either sides of the collector terminal through a capacitor builds up the feedback path of the circuit. So we'll name them. VCC is for biasing voltage, RC1, RC2, R1, R2 resistors, C1, C2 capacitors. Yes, the voltage is tapped across VC1 or VC2 or both. So VC1, VC2 will be acting as the output voltage. So there are coupled pairs of R1, C1, R2, C2, and these four resistors and the two capacitors operate in such a way that they are capable of generating output waveform. As soon as VCC is given, the capacitors either charge or discharge and give different operating modes. These operating modes we'll discuss now. Base 1, emitter 1, collector 1. This is collector 2, emitter 2, and base 2. Initially, when Q1 is on, Q2 is off. When plus VCC is given, the capacitor C1, which was already charged, starts to discharge. Yes, for plus minus, and the capacitor C2 starts to charge. This is mode 1. The voltage VCC drops across the RC1 resistor, and hence VC1 will be equal to 0 initially, and the point A is at ground potential, and VC2 is equal to VCC. Hence the capacitor C2 starts to charge in this manner, and the capacitor C1 discharges. So when we suppose to draw the key waveforms and understand the operation of these parameters VC1, VB1, VC2, VB2. As said, when Q1 is on, the capacitor C1 is discharging. Initially, the capacitor voltage was at maximum plus VCC. It is discharging, and this is the waveform across it. VB2 is very minimum because it is an on condition. VC2 is charging. So initially the voltage across it was 0 and it starts to charge when Q1 is on. So Q2 is off and VB2 is discharging, and it is this way. Yes, these are the key waveforms during mode 1. Yes, now I am shifting on to mode 2. During mode 2, Q2 is on and Q1 is off. When Q2 is on, VB2 will be low and VB1 will be showing a very minimum value, and the capacitor C2 starts discharging in this manner and C1 starts to charge. So here, based on this, the coupling elements of the resistors R1 C2 and R2 C1 behaves in such a way that the output voltage VC1 changes its state, that is, it starts charging when Q2 is on, and the VC2 starts discharging, that is, it moves from V plus VCC to 0. VC1 initiates from 0 to plus VCC again, and VB1 goes to minimum value and discharges, and VB2 is minimum. These are the key waveforms of a stable multivibrator during this state. So since this condition goes on and off alternatingly, when Q1 is on and Q2 is off, the VCC drops at RC1, VC1 will be equal to 0, and VC2 will show a maximum voltage of VCC. when Q1 is off and Q2 is on, Vc1 will be equal to Vcc, and Vc2, the voltage drop across that, will be equal to 0 volt, because C2 is discharging and C1 is charging in this mode. So the collector voltage Vc1 and Vc2. So initially Vc1 is 0. When Q1 is off, it shows a maximum voltage. Yes, and Vc2 minimum voltage. When Q2 is on, it is 0, and then it increases. Yes. So these are the curves, output curves obtained when Q1 is off and Q1 on. Here when Q1 is off, Q2 is on, and during the initial time period, let us say T1, when Q2 is on and Q1 is off, and T2 when Q2 is off and Q1 is on. So the total time period T is equal to T1 plus T2, where T1 is equal to 0.69 times of R1 C2 and T2 is equal to 0.69 times of R2 C1. Yes, therefore the total time period that we obtain from the output waveform generated by the astable multivibrator is T is equal to T1 plus T2 is equal to 0.69 times of R1 C2 plus R2 C1. If R1 is equal to R2 is equal to R and C1 equal to C2 is equal to C, then the total time period T is equal to 1.38 times of RC, and from this F is equal to 1 by T is equal to 1 by 1.38 times of RC, where F is equal to 0.7 by RC. Yes, some of the basic applications of a stable multivibrator are low clock frequency pulse train in relaxation oscillators. They can be used as relaxation oscillators as they generate continuous pulses like this. So what is the waveform that could be obtained? Since it is not in a stable state, continuous train of pulses are possible in a stable multivibrator. They are used for vehicular indicator lights in early oscilloscopes and television receivers for timing signals. Yes, so these kind of continuous train of pulses can be obtained in timing pulses signals. These are the different applications of a stable multivibrator. The next video will discuss about monostable multivibrator. Thank you.